So let's talk about noise. Noise is any signal that contains no useful information. It's a signal that masks the useful signals. And we can make that a little bit more formal by saying that this is a random signal. The samples of the signal x of n are random variables, and that this random signal is independent of any signal that we actually care about. So let's talk about random variables a little bit. Random variables can be either discrete or continuous. A discrete random variable is a random variable that can only take one of a finite number of values or possibly one of a countably infinite number of values, like all integers. And the complete information about a random variable is given by its probability mass function, or PMF, which is just the probability that x takes on any particular value a. A continuous random variable can take on one of any value in an uncountably infinite set, like the real numbers. And a continuous random variable, its probability distribution is given by a probability density function, which is the derivative with respect to a of the probability that x is less than or equal to a. This is not a probability itself. The probability density is just the density of probability within some range. All right, so noise. Usually in audio, we're talking about zero mean noise, and it's convenient also to base everything else on something called white noise. And here's a picture of a zero mean noise signal. This is actually a zero mean white noise signal that I generated. Zero mean just means that the expected value of x of n is zero. And you can see in this particular signal, the samples are equally distributed above and below zero. White noise means that each sample is uncorrelated with every other sample. It means that the expected value of x of n times x of m is equal to the product of the expected values of those two samples, which is equal to 0 when n is not equal to m. And when n is equal to m, it's equal to the variance, sigma squared. Often we'll need to talk about zero mean white Gaussian noise, and Gaussian just means that x of n is distributed with a normal distribution. The mean is 0 and the variance is some number sigma squared. And that notation, the curvy n notation, means that the probability density function has the form of a Gaussian, a bell-shaped curve. And here are some pictures of Gaussians from Wikipedia. The red one is a Gaussian with zero mean and unit standard deviation. For that particular Gaussian, about a third of the values are between 0 and +1, about a third of the values are between 0 and -1, and the other third of the values are out beyond plus or minus 1. So why do we care about zero mean Gaussian noise? The reason is that in audio, it's a good model for a great variety of interesting signals. For example, fan noise is very effectively modeled as zero mean white Gaussian noise. Babble is zero mean Gaussian noise. Babble means many people talking at once, and you might have heard of this thing called the central limit theorem, which says that if you add together a large enough number of random variables, the resulting random variable starts to look Gaussian. By the way, this is not white noise, it's more like pink noise, meaning that each sample is correlated positively with the sample next to it. Of particular interest in this class, zero mean Gaussian noise is a good model of unvoiced speech sounds. So F and P are close to white noise. Sounds like s, sh, t, and so on have a more high-pass coloration, not quite white noise. All right, so if we're going to have to deal with these signals, let's talk about their Fourier transforms. The Fourier transform of a zero mean Gaussian white noise signal, we can calculate using the Fourier transform formula. It's the sum over little n of x of n e to the minus j k omega naught n. And let's divide that up into the cosine part and the sine part. And now we see that the Fourier transform has a real part and an imaginary part, and the real part and the imaginary part are each a weighted sum of random variables. And a weighted sum of random variables is itself a random variable. So the Fourier transform of a white noise signal is itself a random variable. All right, so we can find its expectation. The expected value of x sub r of k is the sum over little n of the expected value of x of n times cosine k omega naught n, which is just 0, because the expected value of x of n is 0. Similarly, the expected value of the imaginary part is also 0. So the Fourier transform of a zero mean noise signal is itself a zero mean random variable. That's useful and interesting, but not very useful. I mean, things that are zero are just zero. That's the end of the story. So let's talk about its variance. The variance of the real part is, well, it's equal to the expected value of the square of the real part, because the mean is zero. And you know that when you square a summation, you have to take into account all the cross terms between the different elements of the sum. So in order to square xr, we need to take the sum over m of the sum over n of the cosine k omega naught m times the cosine k omega naught n times the expected value of x of m times x of n. And here's where the fact that it's white noise comes into play. The expected value of x of m times x of n is 0, unless m equals n. So all of the cross terms drop out, and we just get the summation over little n of sigma squared times the cosine squared of k omega naught n, which is just the average value of cosine squared, that's 1/2, multiplied by capital N samples, multiplied by sigma squared. Similarly, the variance of the imaginary part is n times sigma squared over 2. And that 1/2 is kind of interesting because if we take the expected value of the magnitude squared of x of k, we get the expected value of the real part squared plus the imaginary part squared, which is just n times sigma squared. This is the reason why the signal is called white noise. White noise is called white noise because the expected value because having a correlation, which is a delta function, means that the expected value of the magnitude Fourier transform squared is 1. It's constant at all frequencies, flat, like the spectrum of white light, and that's where the word white noise comes from. So finally, we have something non-zero that characterizes this signal. We call this something the power spectrum. For white noise, the power spectrum is 1 over capital N times the expected value of the DFT quantity squared. For other signals besides white noise, we need to be a little bit more careful in defining the power spectrum. And so let me now be a little bit more careful. Let me talk about the relationship between autocorrelation, the power spectrum, and the periodogram. The autocorrelation of a random signal is the expected value of x of m times x of n plus m. In particular, this is the autocorrelation of a stationary signal. In this class, everything that we talk about will be a stationary signal, which is to say that the autocorrelation doesn't depend on m. It only depends on the difference between the two samples. The autocorrelation is not itself something we can measure. It's actually a parameter of the random signal. Things that we can measure include the signal autocorrelation. The signal autocorrelation, rather than being the expected value of x of m times x of n plus m, it's just the sum from m equals minus infinity to infinity of x of m times x of n plus m. And you can see how this is proportional to the autocorrelation, but itself, this is a random variable. For any particular value, any particular time that we run the experiment, we'll get a particular set of samples x of n, and so the signal autocorrelation could be different each time we run the experiment. It might not be exactly equal to the true autocorrelation on any given run of the experiment. The signal autocorrelation is useful if you have an infinite number of samples, but on a computer you never have a truly infinite number of samples. And so we need to compute something more DFT-like. We get that with the circular autocorrelation. And the circular autocorrelation is just a finite length window of samples, capital N of them, which are correlated with each other with a circular shift. The circular shift operator is n plus little m modulo capital N. So this is like taking the circular convolution of x of n with itself. And the signal autocorrelation is like taking the convolution of x of n with x of minus n. And we learned in talking about filtering that when you convolve in the time domain, that means you multiply in the frequency domain. And so it's worthwhile trying to find out what is the Fourier transform of the signal autocorrelation or of the circular autocorrelation. To do that, we need to plug x of minus n into the Fourier transform formula, and we discover that the Fourier transform of x of minus n is actually x of e to the negative j omega. That is, if you flip it in time, you also flip it in frequency. If the time domain signal is real valued, then x of minus omega is the same thing as x complex conjugate of plus omega. which means that when we convolve x of n convolved with x of minus n, we get x of e to the j omega multiplied by x star of e to the j omega, which is the magnitude squared of x of e to the j omega. So suddenly we discover that this signal autocorrelation has as its Fourier transform something that looks kind of like what we called the power spectrum before. In fact, the power spectrum is the Fourier transform of the autocorrelation. The true statistical autocorrelation, the expected value of x of m times x of n plus m, if we take the discrete time Fourier transform of that signal, we get something that's called the power spectrum. This is a parametrization of the random signal. It's not something we can actually measure. It's something that we have to, that knowing this value, we could generate the signal, but knowing an instance of the signal, we can't find this value exactly. Instead, we estimate it by computing things like the signal autocorrelation and its Fourier transform, the DTFT periodogram. The signal autocorrelation has as its Fourier transform something that we call the periodogram. And the periodogram can be computed either with an infinite length signal as shown here, or we can compute the periodogram with a finite length signal using circular autocorrelation, in which case we call it the DFT periodogram. The discrete Fourier transform of the circular autocorrelation is the DFT periodogram.